Hello guys, how's it going? Can you hear me? Okay, it seems like I can see myself, so it seems like everything's fine. Hi, how was today's contest, guys? How many problems you guys solved? Did you enjoy today's contest? Sound is not good. Is the sound fine or not? Worse in month. Okay, let me see. Is it by any chance better now? If there's an issue with sound, let me know. Otherwise, we can start discussing the problems. It's fine. Okay, so let me know if there was any issues with my sound. I can maybe try to disconnect the microphone. It should do good, but I don't know what's wrong with it. I must not have an echo. Let me disconnect the microphone. Better now? Let me just make sure that the sound is high enough. Okay, much better. Nice. It's weird that the microphone is not working good. So, okay then let's start discussing about the problems. We're gonna discuss problems A to E today, A to E1 today. And maybe if you wanted, we can also try to understand people's solution on problem E2 as well, if anyone needed that. So let's discuss this problem A1 first. It says that you are given a cyclic array A1, A2 to AN. You can perform the following operation on A at most n-1 times. Let n be the current size of A. You can choose two adjacent elements such that the left one is less than the right one and it is circular. So the last element is to the left of the first element as well. And remove one of them as you choose. And at the end you want to make all the elements equal. What is the minimum number of operations needed to do that? So we have this circular array. And each time we can choose two of them, 1, 2, 3 to m. And if the left one must be less than the right one, and remove one of them as we choose. We have to say that what is the minimum number of operations needed to make all the elements equal. Well, I want to show that the answer is going to be n minus the maximum number of appearances of a number. So you should see that what number has appeared the most, any number like x, and the answer is going to be n minus that one. Or in other words, for every x, I am able to remove everything else except x. Everything except x. Okay, so I want to prove this. For every x, if I only consider the occurrences of x, I can remove everything else other than these x's. How do I say that? I just say that, okay, assume that I have these blocks of x's. Well, I want to show that each time I am able to remove at least one element that is not x. If I show that, then everything is proved. So if I show that at any moment I am able to remove one element that is not x, one element that is not x, then it shows that I can keep repeating this operation, each time I remove one of them. So it's just enough that if I show that I can do one operation in which one element that is not x will be removed. If I show this, then each time, as long as while there is, I can just have a while, and I can say that while there is an element, there still exists an element that is not x, remove at least one of them, remove one of them. If I show that I always can remove one of them, then I can keep repeating this operation as long as at the end there is not gonna be any elements that is not x. So everything left is x. I want to keep all the x's and remove everything that is not x. How do I prove this? Well, there are two cases. Either I just have, if I consider my x's, either there are just one block of x's, or there are more than one block. And these two cases are similar. In both ways, I can make an array such that the first element is x and also the last element is x. Even in this case, because the array is circular, I can start from here and come back to here. And the first and the last element can also be the same. That is okay. So I want to show that it is always possible for me to consider a subarray such that the first and the last element is x. Okay, and nothing in the middle is x. It is always possible. So if I have an x, how do I make this? I start from one of the x's. I know that I must have at least one x, because I want to keep all the x's remain in my array. So I choose an x that I have at least one of it. I start from it and I go forward as long as I'm not seeing any other x. When I see another x, I will stop. So this way I have an array that the first element is x and the last element is x and nothing in the middle is x. Okay, and there is at least one element in the middle. I can just choose an x such that its next element is something that is not x. This way at least one element is in the middle, right? So I have at least one element that is not x in the middle. The first element is x and the last element is also x. Then what do? I just say that I want to show that I can choose two elements in here such that the first one is less than or equal to the second one. The left one is less than or equal to the right one. And do not forget that, as I said, this x also can be this x itself as well. That is also okay. There's no problem with that. If I show that there are two elements that I can choose them, then I can say that I can choose these two elements and at least one of them is not x. At most one of them is the first one or the last one. So at least one of them is not x and I can remove that. How do I say this? It's just enough to say that, well, my first element is x and my last element is also x. If I consider the values of the numbers, when I cannot do an operation, when the next element is less than the previous elements. So I should have a strictly increasing array in here if I can never find two elements such that the first element is less than or equal to the next element. But I see that the first and the last elements are the same, so this is not possible. This is a contradiction. So this array is not strictly decreasing. So I start from an x, I go forward till I reach an x. That can be the same x or another x. And I know that there's at least one element in here that is not x, because I know that there's at least one element that is not x left. So I choose this block in a way that at least one of those elements that are not x will be in there. Then I say that if I cannot do any operation in here if and only if this is strictly decreasing. But that is not possible because this array is not strictly decreasing. I see that the first and the last element are the same because the first and the last elements are the same. If it was strictly decreasing, it was not possible. And because the length is at least 2, there is at least one x and one non-x elements. Therefore, I can find two elements that the first one is less than or equal to the second one. And at least one of them is not x, because no two adjacent elements are x. So I can find two elements like this, and I'm not considering this array to be circular. I just want to find two I consider them on a line. I want to choose two consecutive one of them, and I know that at least one of them is not x. Therefore, I can remove the one that is not x. So this shows that I always for each x I can always remove one element that is not x. And do not forget that it is enough if I show that I can remove one element, because if I show that I can remove one element, I can keep repeating this operation until there's nothing other than x. This shows that if I find so now for each x I know that I can make everything else, I can delete everything else other than these x's. So the only thing I need to do is to find the x that has appeared the most number of times. For example, if x has appeared v times, my answer is gonna be n minus v. So it's enough to find the maximum number of v, maximum value for v, and my answer is gonna be n minus that v. And this way easily I can solve problem A. So it has a little bit of theory, but its final implementation is very easy. I just say that it's enough that I see in n and I have some value mx, that is maximum number of times that an element has appeared. I see in all the AIs, and whenever I received an AI, I say that CNT of AI plus plus and mx is equal to maximum of mx and CNT of AI. And then I see out n minus mx. That is gonna be my answer. And then I will make all the CNTs 0 for the next test case, because I should initialize everything for the next test case afterwards. This way I can easily solve the problem. And if you do this, you will get accepted on this problem. Is it clear? I'm not sure if this question is from me, but if it is, you know, the main intuition behind this was how to, if I have some x, I can remove everything other than x. By seeing this problem, by seeing this operation, this kind of gives you the feeling that if you want to keep x left, it's the best if you do not remove any of the x's and remove everything else. So the point is that you want to keep as many elements as possible. When you want to delete the minimum number of elements, it means that you want to keep the maximum number of elements. So you need to, and for each x, if x is the number that you want left, you want x's to be left, it's the best if all of them are left. The best thing for you is that if all of the x's are left. Therefore, the best thing for you, I mean, if you can show that I can keep all the x's, that is going to be the best case for you. So this is how you get to this solution. If it is clear, please use this emoji or say that in the chat. And if you need re-explanation, also say that in the chat. Nice. Nice. Thank you. Thank you for all the random emojis. Okay, nice. So let's move on to the next problem. Problem B, generates permutation. This problem says that we have an integer sequence. This problem statement was a little bit hard. I saw that one of you mentioned it, and I also believe in that. For me also, it took a little bit to understand what it wants exactly. There is an integer sequence A of length n where each element is initially -1, and you have two typewriters. Each time, you know, the first typewriter is to the left and the second typewriter is to the right. Each time you can write anything in any of these pointers. If there's no number there, you want to create a permutation. You can write a number in those positions. If that position does not have a number yet, its value is -1 right now. Initially all of them are -1. It means that they have no value. You can write a specific number, you can choose it, and you can write an arbitrary number there, or you can move the pointers, or you can reset the pointers, move them to where they were from the beginning. The left one should go to the leftmost position, the right one must go to the rightmost position. And then you need to choose one of these two typewriters. Either always choose the left one or always choose the right one. And you want to find a permutation such that if you see that what is the minimum number of times that you return the pointer to its initial position, you want to minimize that. You want to minimize the number of these operations, that you return the elements to where they were. You want to find a permutation that the number of times that you use this will be minimized, and you want to find a permutation that these two minimized values are the same for the first typewriter and the second typewriter, for the first pointer and the second pointer. In other words, you want to find the permutation such that if you use the right pointer always, or if you use the left pointer always, the number of times that you will return them in their initial position will be equal. The minimum number of times that you will return them to their initial position will be minimum. You want to find a permutation that this value is the same for both of them. Is it clear? Is the statement clear? I know that this statement must be a bit problematic. So first, let's just make sure that you're all okay with the problem statement. If anyone is not okay, let me know. It is not clear. No problem. So let me explain it to you in another way. So you have two pointers, you have two typewriters. The first one writes letters from left to right. And its pointer is initially pointing to 1. Another one, the second one, writes from right to left, and its pointer is initially at point N. You will choose one of these two and write with them. For example, assume that this is, for example, your permutation. For example, your permutation is 5, 1, 4, 2, 3. Assume that you want to start from the first, you want to use the first typewriter. Its pointer is at point 5. Each time I said that you can use write an arbitrary number. I was wrong, sorry. You can write the minimum number that is not used yet. You cannot use an arbitrary number. So if you want to use the first typewriter and make this permutation, as I said, initially all the numbers are -1. So they have no values first. Each time you can, when you are at the index that its value is -1, you can write the minimum number that is not used yet on that position. And you want to make this permutation. Well, how can you do that? The way you can do that for this array, if you use the left pointer, is to first you start from this pointer. First, you know that the first number that you're going to write is 1. So first you need to move your pointer to here. Then in here you can write 1. Then you can move your pointer to here. Do nothing. Then move your pointer to here. And in here write 2. Because 2, you can write 2. 2 is the minimum number that is not used yet. Then you move it to here. And you'll write 3. Then you need to return it to its initial position. Because now you want to fill these two positions in the first index and the third index. So now you will move it to the first index. And then again, do nothing, move it to the right, move it rightwards. Then do nothing, move it rightward. And in here now you can write 4. Then again return it to the first position, so it is the second time that we return it to its initial position. And in here now write 5. Okay, so now this way, how many times I used this return operation? I used it twice. So the number of times that I used it was 2 times. Also, if I use the right typewriter, if I want to create this array with the right typewriter, it is gonna be like this. Initially all these values are -1. You start from here, you do nothing, move it here, then here, then here, and here you make it 1. First you need to set the value of 1, so you have to move it to 1. Then you will return it to its initial position. Then move it here, and here write 2. Then move it to initial position. It's the second time that you're using this. Move it to the initial position. Now in here you can write 3. And then move it here and write 4 here. And then move it here, you write 5 in here. So you saw that the minimum number of times that you could use return for the first pointer was 2. Also for the second pointer was 2. So for both of them was 2. So these values are the same. They are the same in 2 cases. So this is a correct answer for n equal to 5. In this permutation, if you want to minimize the number of returns, whether you use the first typewriter or the second typewriter, both of them, the minimum number of returns for this permutation is 2. So they are the same. So this is going to be an answer for n equal to 5. Is the statement clear now? Is it clear how the typewriters are being used? If it is clear, please use this emoji or put a plus. Nice. Your ears, is the voice high? Or nice. Wait a second. Yes, now I will explain how to find the answer. Okay, so now what do I say? I say that where do we use this return? Assume that, let's talk about the first pointer. And then we see that for the second pointer it's gonna be exactly like this, or the first typewriter. Let's talk about the first typewriter. Where do you use return? Well, the point is that when you want to write an X and then you see that x plus 1 is before x. So you have to, you consider x and x plus 1, and consider that x plus 1 comes before x. The point is that first you need to, when you write x, your pointer is here. Your pointer is here. Then you need to write x plus 1, and x plus 1 is to the left of x. So you need to return your pointer to the beginning. Do you agree? So the point is that if x plus 1 is before x, for that you need to return your pointer to the beginning. For example, as we saw in here in this example, when we wrote 3, we saw that 4 is before 3. So for that, you know, our pointer was here when we wrote 3, and after that you need to return it to point to the beginning of the array again. You need to move it to the beginning of the array again in order to move it to 4 and to the position of 4 and write 4 there. So I can say that the number of times, the number of returns needed is gonna be equal to the number of x plus 1s that are before x. So you need to see that for how many x plus 1 is before x, and you want to find out for how many x's x plus 1 is before x, and that is the number of times that you need to return it. For example, here 4 is before 3, so for x equal to 3 it happens, and for x equal to 4, because 4 is before 3 and 5 is before 4. So for them, when you write x afterwards, you need to return the pointer to the beginning and then move it forward to the position that x plus 1 is and write x plus 1 there. Do you agree with this so far? If you agree with this, please again use this emoji. Nice. So this is for x. X plus 1 must come before x. Nice. Now assume that you want to find the number of times that the second pointer. Now let's talk about the second pointer. For second pointer, for second typewriter, that is also the same. For the second typewriter, you can also say that you need to find the number of x's that x plus 1 is after x. Then you need to move your pointer to here to write x, and afterwards when you want to write x plus 1, the next time when you want to write x plus 1, you need to return it to the beginning and move it back again to where x plus 1 is and write it there. And as you see in this example, when we wanted to write 2, we need to return our pointer to the beginning, because before we were here and we wrote 1 here, now 2 is after 1, so we need to go rightwards. So we need to return this pointer to the beginning here, and then move it to where 2 was and write 2 there. Therefore, and also about 3, then we come here and write 2, and then for 3, you know that 3 is here, so we need to return our pointer to the end and go to where 3 is, which is exactly where the last element, and write 3 there. So you can say that in this time the number of operations is going to be equal to the number of x plus 1s that are to the right of x. So the number of x plus 1s that are to the right of x. And as you can see in here, for example, for x equal to 1 it happens, and for x equal to 2 it happens. You see that each x is either here or here, because for each x, either x plus 1 is to the right of it or x plus 1 is to the left of it. So it will be counted in one of these two cases, because x plus 1 is either to the left of it or is to the right of it. So for example, for x equal to 1 and x equal to 2, x plus 1 is to the right of x, so they will be counted here. For x equal to 3 and x equal to 4, x plus 1 is to the left of them, so they will be counted here. Okay, so this is how we will find the minimum number of returns needed. Okay, is it clear so far? We haven't yet talked about how to now find the desired permutation, but is it clear so far that how we can see the answer is? If it is, please again use this emoji, use the emoji, or say that in the chats. Nice. Nice. So now, thank you. Great. Now, this easily shows that if n is even, you know, how many pairs of x and x plus 1 do you have? How many x and x plus 1s do you have? It is exactly n minus 1, right? Because we have 1 and 2, we have 2 and 3, we have 3 and 4, 4 and 5. These are our x and x plus 1s that we have. And n minus 1 and n. The number of these pairs is exactly n minus 1, right? The number of these pairs is exactly n minus 1. So we have n minus 1 pairs, n minus 1 such pairs. This, and we know that each one of them either will be counted here or in here. And we want to make them equal. We want these two to be equal. So exactly we want half of them to be in this case, half of them to be in this case, right? So that easily shows that if n minus 1 is odd, or in other words, it means that n is even, there is no way, because you have even x and x plus 1s and you want to split them into two equal groups. There's no way to do that. There are even number of elements. There's no way that you can split them into two equal sets. Right? So if n was even, the answer is definitely minus 1. But if n was odd, we want to construct a permutation such that exactly for half of x's, x plus 1 comes after x. For half of them, x comes after x plus 1. So we want half of them to be like this. There are exactly n minus 1 of these pairs, so you want n minus 1 over 2 of them to be like this. N minus 1 over 2, let me write it like this so that it wouldn't be ambiguous. And n minus 1 over 2 would be like this. How can we create that? Well, you can simply create it like this. For example, you can construct an array like this. You can first write n, and then 1, then n minus 1, then 2. So maximum, minimum, maximum, minimum, maximum, minimum each time among the remaining numbers. N minus 3, 3, n minus 4, 4, and so on. For example, assume that n is 7. For n equal to 7, it would be like this. For n equal to 7, it would be like this. 7, 1, 6, 2, 5, 3, and 4. And what happens this way? You can see that for any x less than or equal to n minus 1 half, x plus 1 is gonna be after x. You see that for 1, for 2, and for 3, for all the x's less than or equal to n minus 1 half, x is before x plus 1. Because if you see these numbers, these are all the numbers less than or equal to n minus 1 half. And n plus 1 half is gonna be the last elements. Because this is the middle elements. That's, you know, its value is the middle one among numbers from 1 to n. And it comes last. So all the numbers less than it, all the numbers less than this, x plus 1 is after x. And for each x from 1 to n minus 1 half, it's like this. For any x between n minus 1 half plus 1 or n plus 1 half, this last element, to n minus 1, x plus 1 comes before x. And you can see that this is exactly n minus 1 half numbers, and this is the other n minus 1 half numbers, the other n minus 1 half pairs. So exactly you see that for half of them, the first one, x comes before x plus 1, for half of them x plus 1 comes x. And this way you can simply say that this has the condition that you wanted. And so it's going to be your answer. Let me also show you the code to further clarify this. If you see this code, I see in n, first I say that if n and 1, if n was odd, if n was not odd, else just see as minus 1. It is not possible. But if n was odd, you can have a for I from 0 to I n half. Each time write n minus I and then I plus 1. For example, when I is 0, first you write n, then you write 1. When I is 1, first you write n minus 1, then you write 2. When I is 2, first you write n minus 2, then you write 3. And so on. And then you will see out the middle elements, n plus 1 half. The one that is exactly, its value is in the middle, but in our array, in our permutation, comes last. And this will create what we wanted. For example, when it is 3, you start from maximum, then minimum, then maximum, then the middle one. 2 is going to be the middle one. Or, for example, when your n is 9, your n, if your n is, for example, 9, you write maximum, minimum, maximum, minimum, maximum, minimum, maximum, minimum, and maximum. This is the middle one that comes next. Then for every x as 1, 2, 3, every x less than or equal to n minus 1 half, you will see that, sorry, this is 4, 5, I'm sorry. Maximum, minimum, minimum is here, is 4 here, and then maximum. This is the middle element. So for x equal to 1, 2, 3, and 4x plus 1 comes after x. For x equal to 5, 6, 7, and 8, x plus 1 comes before x. So these are going to be the cost for the second one, for the second typewriter. This is going to be the cost for the first. This will contribute to the cost of the first typewriter. And this way, these two typewriters are going to have the same cost. Is it clear? If it is, please again use this emoji or write in the chat. If it is not clear, also write in the chat. It's okay. I mean, there's no issue that it computes n half each time, because it's so fast. I mean, there's no issue with that. Yes, you can also save it in a variable and just put that variable in here, but that wouldn't make any meaningful difference in the time that your code will consume. Okay, so shall we move on to problem C? If there is no questions, can you explain the maximum part again? Yes, I'm right. I'm saying that the permutation that you will make, it will be like this. First you put n is your maximum number. Then you write 1 is your minimum number. Then you write the maximum remaining one is going to be n minus 1. Okay, it doesn't write. Then you write the maximum remaining element, which is n minus 1. Then you write 2. Then you write n minus 2. Then you write 3. Then you write n minus 3. Then you write 4, and so on. This was the maximum part. Maximum and then minimum. Then maximum and then minimum. Then maximum and then minimum. This way, for all the numbers like x that are less than or equal to n minus 1 half, you're gonna have x plus 1 after x for all the numbers greater than n minus 1 half, and obviously x is between 1 to n minus 1 as well. X plus 1 comes before x. These will contribute to the second typewriter. These will contribute to the first typewriter, to the cost of the first typewriter. This way we are sure that they are going to be the same values. Is it clear? No? Okay, sure. Let's move on to problem C. Problem C, guess the tree. This is an interactive problem. We have a secretary and they are indexed from 1 to n, and you have to guess the tree. You have to find the tree by asking these questions. Each time you can ask two A and B's, and the answer to this would be some node x that minimizes d of A and x minus d of B and x, where d of x and y is the distance between nodes x and y. If more than one such node exists, Mitsuki will tell you the one which minimizes d of A and x. So you want to find the one that's the difference, the absolute difference of d of A and x and d of B and x is minimal. And then among all of them that minimize this value, you need to find the one that minimizes d of A and x. You need to find out the structure of Mitsuki's secretary using at most 15 n keywords. N is up to 1,000. What do we do on this problem? Well, we know that when we ask A and B, the answer is going to be a node x such that it minimizes d of A and x minus d of B and x. Let's figure out what exactly this x is. I mean, what does it mean that it minimizes this value, d of A and x minus d of B and x? Well, the point is that if you consider the path between A and B, the node that is going to be in the middle of this path is going to minimize this value, because either the length of this path, the number of edges in this path is even. For example, assume that the distance between A and B, let's say the distance between A and B, let's call it, for example, I don't know, for example, H, for example. Or let's call it L as length. Stands for the length of the distance between A and B. If L is even, exactly L half edges will be here, L half edges will be here. And the difference between these distances is going to be 0. And L is, if L is odd, one side will be L minus 1 half, one side will be L plus 1 half. So the difference will be 1 exactly. Now we know that among all such x's, Mitsuki will choose the one, the x, that minimizes d of A and x. So the point is that not only this node is gonna have the minimum absolute difference between distances from A and B, but also the nodes in the subtree of it. I mean, if a node is here, for example, also for this one, the distance between this vertex and A is the same as the distance between this vertex and B. For example, if L is odd, even. And if L is odd, it also its difference will be 1. But because we find such an x that minimizes d of A and x, we will definitely choose this one over this one, because this is closer to A. So this way we are sure that if L is odd, we will exactly find the middle vertex of the path, of their path. These vertices below the middle vertex, below the middle vertex, are also have this situation that their distance from A and B are the same. But the point is that among all such vertices, Mitsuki will return the one that minimizes the distance to A as well. So this is gonna be, in case that L is odd, L is even, it will return the middle vertex of the path from A to B. There's a unique path from A to B, and it will return the middle vertex. Also, if L is odd, again Mitsuki is gonna choose, this way we have two middle vertices, such that they are gonna be exactly L minus 1 half edges here, L minus 1 half edges here, and one edge here. In this case, Mitsuki will return the one that is closer to A. This is A, this is B. Mitsuki will return the one that is closer to A, because for both of them the difference of distances from A and B is gonna be 1, but this left one is closer to A. And also, if you consider the ones that are below this or below this, they are gonna have even more distance from A. So anyway, X is gonna be the middle vertex of the path from A to B, and if there were two middle vertices, Mitsuki will return the one that is to the left of the other one. It will return the left middle vertex. So if we simplify the definition for X, we can say that each time that we ask A and B, we ask like A and B, we will receive the middle vertex in the path from A to B. And if they were two, we will receive the left one. Is it clear so far? So far, is it clear that what we're saying? If it is, please again use the emoji or put a plus. If it is not, put a minus or tell me that it's not clear. Yes, I can give examples. Sure. So for example, let's consider that this is your vertex A. Let me make this a bit bigger. Assume that this is A, this is B. And between them, there are these vertices. R3 is like this. R3 is like this. So this is R3. You know, the only condition for a tree is that we have n vertices and n minus 1 edges, and it is connected. And it also has no cycles. If it has two of these conditions, the third one will be there by default. So if you consider this, what is the distance between A and B? It's going to be 1, 2, 3, 4, 5, 6. The distance between A and B is 6. I'm saying that the X that minimizes the distance from the difference of the distance from A to B is going to be this middle vertex. For all these vertices, this middle vertex of the path and all the vertices below it, the distance to A and the distance to B are the same. So this value that we want to minimize is going to be 0. This value that we want to minimize. But among them, we will choose the one that is closest to A. Which one is closest to A? This one. So in other words, I'm saying that each time when we give A and B, it will return to us the middle vertex of the path from A to B. That is what it will be returned to us. Also, if the distance was, for example, an odd number, again, I've added one more edge, for example, in here. Now the distance is 7 instead of 6. Now, for this vertex, the distance to A is 3, the distance to B is 4. For this vertex, the distance to A is 4, the distance to B is 3. And also for all the vertices below it, if, for example, there are several vertices in here, also for these vertices, that's the same. The distance to A is 1 more than the distance to B. But still, we will not choose these vertices because, again, this one is the closest one to A. So if there were two middle vertices, we will choose the left one, the one that is closer to A. Okay, is it clear now? So all I'm saying, I tried to figure out what x is. I showed that x is going to be the middle vertex of the path from A to B. And if there are two middle vertices, it will be the left one. Nice. Nice. So how do I use it? Well, I say that let's make our tree rooted. Let's make our tree rooted at vertex 1. So we have a tree, we can make vertex 1 the root of this tree. Vertex 1 is the root of our tree now. Okay, we can choose any arbitrary node and set that as the root of our tree. Now, each vertex has a parent. If you're familiar with the trees, when you make a tree rooted, each vertex has a parent. And if we find the parents, then we're gonna have, if we find the parents, we're gonna have our tree. We know that what exactly our tree is. Okay, so the point is that if you find the parent of each vertex, you're gonna know that what your tree is. So what you can do is to find for each vertex, like vertex V, you want to find what is the parent of vertex V. How can I do that? Well, this is when this 15 comes into place. This 15, if you see this 15, what feeling does this 15 give to you? This 15, when you see n is also up to 1000, this gives you a feeling of log n. This is a value that is greater than log n. And how this is gonna be useful? I mean, both this 15 gives you the intuition of log n, and also the fact that each time you will get the middle vertex of a path. This also gives you a feeling of some sort of like binary search, you know? I mean, this is how the intuition can be built. Both that 15 number, that 15 that we see there, and also the fact that we're talking about the middle vertex in here. Both of them give us the feeling that there's some log n here. And how do I say that? I know that vertex 1 is an ancestor of V, right? Vertex 1 is an ancestor of vertex V. Now I say that each time, let's query 1 and V and 1. Let's ask V and 1. It will return the middle vertex from V to 1. Now this is another ancestor of V that is closer. I mean, if you see the distance from V to this vertex is around the half of the distance from vertex V to 1. So now you have another ancestor of V. Next time, let's ask V and this vertex. Then this gives you another ancestor. Next ask V and this vertex. This gives you another ancestor. Next, and keep doing that until it's the answer of your query is gonna be V itself. When you reach a vertex X such that if you ask X and V, V itself will be returned, it means that X is the parent of V. So we will keep doing this. Until we get V itself, and it means that the previous vertex was the parent of X and was the parent of V, and this way we are gonna find the parent of vertex V, and that can help us find the parents of all the vertices. And how many times this operation will take time? It will take at most log of n times, because you see that the distance from this vertex to its ancestors will be halved each time. And this way you're gonna find the parent of each vertex. Is it clear? Oh, thank you guys. You don't need to do this, but thank you a lot for your support, Kartik and Yoman. Thank you a lot. So if it is clear, please use this emoji or put a plus in the chat. If it is not, let me know. So this was the main idea. If it is clear, then we will move on to the code to explain it further. Okay. So as I said, it's just enough to start from V. We can just keep a variable like as ancestor. We can keep it as a variable like A, which is our ancestor, which is an ancestor of A. Each time I want to move A closer to V, I know that each time I can move A to the middle point between A and V. This also gives us the intuition of that logarithm. So each time I will ask V and A, if it was equal to V, then it means that A is the parent of A is the parents. It happens if and only if A is the parent of V. If A is not the parent of V, the middle point will never be V, because there is at least one vertex in between them, and the middle point is not going to be V itself. Otherwise, set A equal to the result of it. If ask of V and A was X, set A to X for the next time. If it was X, set A to X for the next time. And keep repeating this. This operation will take log of n time. So let's move on to the code. As you can see in the code, we just do this. We see in n and we see in, first of all, let's see in n and we set the parent of each vertex to -1. Now, vertex 0, I'm using 0-based indexing in my code. Vertex 0 is the root. For vertices from 1 to n-1, we need to find their parents. I set last equal to 0. Last is the A that I was talking about in my tablet. It is the last ancestor that I had. Initially, it is 0, the root of the tree. Each time I set x as ask of I and last. Do not forget that it is not last and I, it's I and last. Why it is not last and I? Because if I use last and I, in case that the distance is even, it will return the one that is closer to last. But I want that if they were equal for two vertices, it will return the one that is closer to vertex I. I say x equal to ask of I and last, and in my ask I just ask the a plus 1, b plus 1 I see in x, the answer of it, x minus minus, return x. X minus minus is to make it 0-based indexing. If x was equal to I break, I found the parents. Otherwise set last equal to x, and this do while true is exactly while, but this way we just make sure that it's will be executed at this once. In this implementation, it has no difference with while. We could also say while true instead of do while. Previously, I was trying to implement it with a little bit difference, but when I change it, there's no difference. I could just say while true in here instead of do while. Each time I ask this, and if it was equal to I will break, and I set par of I equal to last at the end. And at the end, it's just enough to, for each vertex from 1 to n, just see out the edge between par of I and I. And this way I have my whole tree. And if you do this, you get accepted. Now it is judged, and this problem C will be accepted. Is it clear? If it is clear, please again. Use the emoji or put a plus in the chat. Yeah, the code was kind of, it was mostly what, if you reach the idea, then the code was kind of easy. Nice. Nice. Okay. Let's now move on to problem D. For problem D, my solution is not very clean. I'm not sure if there is a cleaner way of implementing this or not, but I will tell you my implementation, my solution for problem D as well. I did not like my own solution a lot on this problem, but let me tell you this. So, problem D says that you are given an integer sequence a1, a2 to an. Let S be the set of all possible non-empty subsequences of A without duplicated elements. So S is the set of all possible non-empty subsequences of A without duplicate elements. Your goal is to find the longest sequence in S, the longest sequence that you have in S among all the subsequences without any duplicated elements. And among them, you want to find the one that is lexicographically minimum if you multiply the ones that are at odd position by -1. Or in other words, what it wants, it says that, for example, among these, 3, 2, 1 would be the answer. Among these sets, the best one is 3, 2, 1. Because first of all, it has the maximum size. 3, 2, 1 and 2, 3, 1 have the maximum sizes. And if you multiply the ones that at odd positions by -1, 3 and 1 at -1, and the position, we only care about the position in S. So we just care about the position in this set, in this sequence, in this subsequence. We put, for example, 1 in the original sequence is at the 4th place and 3 is at the 1st place, but the original position do not matter. We care about the positions in this subsequence. We multiply 3 by -1 and 1 by -1. And then we just when we multiply them by -1, we just now compare all of these lexicographically. -3, 2, -1 is lexicographically smaller than -2, 3, -1. So this is better than this. In other words, it is like we want to maximize the first element and minimize the second element. I mean, first maximize the first element. That is our first priority. Among them, we consider the one that minimizes the second elements. That is our second priority. After that, we want to maximize the third element. After that, we want to minimize the fourth element, and so on. So this multiplying by -1, it's like we're changing the order. Instead of wanting this value to be minimum, we want it to be maximum, as it is. Because, for example, here 3 is greater than 2, -3 is going to be less than -2, so it's going to be better. So it's like for the first position, we prefer it to be greater. For the second position, we prefer it to be smaller. For the third position, we prefer it to be greater. And this is how we compare them lexicographically. And you need to find out that best subsequence. First, it must have, the first priority is the length. The length should be maximal. Then we want to maximum the first element. Among all of them, we want to minimize the second element. Among all of them, we want to maximize the third element, and so on. Is it clear? Is the statement clear so far? So this is the statement of this problem. If it is, please again use this emoji or put a plus. Yes, that is true. The length of the longest subsequence is equal to the number of distinct elements. Yes, that is the first fact on this problem. Exactly. Nice. So, yes, as you mentioned, as the first fact, as fact 1, we can, as fact number 1, we can say that the maximum length, which is our first priority, the maximum length is the number of different numbers in our array. Different numbers in our array. For instance, if you look at these examples, for example, in here we have 3 different numbers, so the length of the answer is going to be 3. Or for example, in this example, we have 1, 2, 5, 7, and 9. So the length is going to be 5. Why? Because at least, we can choose one of the appearances of all of these numbers. When we have different numbers, we can choose one of the appearances of each of these numbers, and this is gonna be, we can choose one of the appearances of these numbers, and this is gonna be a valid array with this length. So as fact 1, the maximum length is gonna be the number of different numbers that we have in our array. Is it clear so far? If it is, please again use this emoji or put a plus. Nice. So this is the first fact that we can say. Now, we want to find the one that is most optimal lexicographically. And what does it mean lexicographically optimal? As we said, we want the first element to be maximum. The second, this is our first priority. So the first thing that you care about is that our first element is maximum. If the first element is different in 2 numbers, we do not compare the next elements, because it is lexicographically. We just consider the first position that they are different. So our first priority is that our first element is maximum. Then the second element must be minimum. Then the third element must be maximum possible. The fourth element must be minimum possible, maximum, minimum, and so on. So my solution for this is we can act greedy. We can act greedily. How can we do that? Well, the point is that one thing that I keep an array named ants. In ants, I will keep the best possible array that I can have so far, the best array sequence that I can have so far, and it is possible for me to continue it in a way. What do I mean that I can continue it? I want to have the best possible array such that I can continue it. By I can continue it, I mean that for each element that is not in my sequence, for each element that is not in my sequence, I want the CNT like x CNT of x, the number of x's that are left, must be greater than 0. I mean that for when we have gone so far and I have made a sequence so far, this is the best sequence lexicographically, the best sequence that I can have so far. Okay, so I say that I must be able to continue it. And what do I mean by that? I mean that, for example, if there are several 5s in here and 5 is not in my sequence, I need to make sure that CNT of 5 in the rest of the array is greater than 0. So I have the chance of adding it in the future. You know what I'm talking about? So I want to find the lexic. So far, I want to greedily find the lexicographically best one for each element that is not in my array yet. I must be still able to add it in the future. If I know that I have at least one of them in the future, well, in the worst case scenario, I can add it then. So it's better, even if I do not use it so far, in future I can add it. So it's best if I focus on making the first elements as high as possible. Okay, so this is the idea. I have a sequence so far. It might not use some of the numbers that it has visited. For example, maybe the first element is 1, then it is 3, there's a 3, and when I'm here, I might pop this 1 and add this 3, and my sequence is gonna be 3, only 3 so far. but only if CNT of 1 is here in here is greater than 0. There is one additional 1 in the future as well. Because if it is not, then I might not be able to add this one back to my sequence again. So in that case, I cannot remove this one. But if I see this 3, and I see that there is another one in the future that I can add in future, then it is better for me to make the first number maximum because it's the first priority, and that one can somehow be added in the future. I do not need to worry about it. So when I see a 1 and then I see a 3, if I have another 1 in the future, if CNT of 1 in here is greater than 0, it means that I have another 1 in the future. So I can just remove this one and add this 3. But if there is no additional 1 in the future, I cannot remove this one. I have to keep it. So in this way, I will not remove 1 and I just add 3 to the end. Is it clear? So is the main idea clear what I'm trying to do? So I'm trying to greedily construct my sequence. I want to greedily construct my sequence such that at the end, the elements that are not in my subsequence, I am still able to add them in the future. So make a counter for each. Yes, exactly. I have a counter for each of them. I have a CNT of x. Whenever I see an x, I say CNT of x minus minus because one x is removed from the rest of the array. Yes. So, okay, so let me explain it again. For example, assume that our array is like this: 1, 3, 4, 2, 1, 2. This is our array. When I start from the beginning, first I'm here, I see 1. So my sequence is going to be 1. The best sequence that I can make so far is 1. Then this 3 comes. I see that this 3 is better than 1 for the first position. And I see that there is another 1 in the future. So I can add another 1 in the future. So I can remove this 1 and instead add this 3. And I do not need to worry about removing this 1 because I have another 1 in the future that I can add it later on. If there is no other 1 in the future, by removing this 1, then I can never have 1 again anymore in my sequence. So if there is no 1 in here, in the future, then if I remove this 1, I cannot add it back again to my sequence. So the length of my sequence is not going to be maximum. In that case, it's going to be bad. I cannot remove 1. Otherwise, I remove 1 and add this 3. Now I see this 4. Again, I see that 4 is better than 3. But this time, if I remove 3 this time, I cannot add it back again because in future I do not have 3. So even though this 4 is better than 3, I will not remove this 3. I will keep it because if I remove it, I cannot in future add it back again. So 3 remains here and 4 will be added afterwards. Then this 2 comes. 2 is better than this 4, but again I cannot remove this 4. Imagine that there was an additional 4 in here. In this case, if there was an additional 4 there, in this case, when I see a 2 comes, I see that 2 is better for this position compared to 4 because it is an even position, and for even position, it's better if I minimize them. So in that case, if there is another 4 in the future, in here, in these parts, I can remove that 4. And so if it is not, I cannot remove that 4. In here, I see that, okay, there is another 4. So I can remove this 4 and add a 2 instead of it in here. This is going to be the best lexicographically most optimal sequence that I can have, and I can continue it. Then I see this 1. Again, I see that this 1 is better than that 2. And I see that I have another 2 in the future, so I do not need to worry about removing my current 2. So I can remove my current 2 and add a 1 here. So As you see, so far this 4 is removed, this 2 is also removed. Then I see another 2. This 2 comes, this is not better than 1, and this is not better than the 3 that I have at the beginning, so I can just ignore them and have them as where they are, and add this 2 to the end. And then this 4 comes. This 4 again is better than this 2, but because I do not have another 2 in the future, I cannot remove this 2. So this 2 remains, and this 4 will be added to the end. So the most optimal sequence that I can have in this case is 3, 1, 2, 4. As you see, it has all the numbers, and I greedily made it lexicographically maximal. Right? Is it clear? Nice. If it is clear, please again use this emoji or put a plus. Let me also read all the comments. Length will be count of unique elements. I have a counter for the length, yes, is the number of unique elements, yes. Yes, this is also true. Maybe, I don't, maybe that would work as well. Yes, I will explain to you how to exactly implement it as well. I see what you're, yeah, maybe there are better solutions. Maybe, yeah. If you had other solutions, you can also explain it in the chats. That I would appreciate it. That would be nice. But this is what I did. So this is the idea. I try to find the most optimal lexicographically optimal sequence so far, such that I can continue it, as you saw in this example. For example, in here you saw that you could continue each sequence that you've made. So how do we update it each time? Well, the point is that when a new element x arrives, you can see your current answer, your current sequence you have. X might be better than the last element or the elements before that. I mean, let's just consider the last 2 elements. Why the last 2 elements? Why not only the last elements? Because maybe x is a very large number, a very great number, and for example, this last number needs to be minimized, and the one before that must be maximized. Or vice versa, x is very small and the last number needs to be maximized and the one before that needs to be minimized. As soon as x is very large, for example, and the last number needs to be minimized and the one before that needs to be maximized, then x is not better than this one. But it is better than this one, and maybe it makes sense for us to remove both of these, and add x here instead. So I run a while. Whenever an x arrives, I run a while, and in this I compare x with the last elements in our sequence, and also I compare x with the one before last. So either the last one or the one before last. I compare it with these two, and do not forget that if I want to put it before the last instead of the last one, the CNT of the last one must be non-zero in the future. So it means that I need to have another one of this last one in the future. If I want to replace it with the one before last, the counter of both of them must be non-zero, because I need to remove 2 elements this way, and I need to be able to add both of them back again. So I can run a while. In this case, CNT of last one must be last one must be, let's call this x and this one y. In this case, CNT of y must be greater than 0 in the remaining of the array. And CNT is pre-processed. Each time when we are over some x, we say CNT of x minus minus, so that we know that how many are left. And in this case, both of CNT x and CNT of y, both of them must be greater than 0. So I consider these two cases. While this was true, I will keep removing elements from the ends. And this is a while, so maybe again after that it will remove several more elements as well. So as long as it can make our sequence better, I will pop from the end of my current sequence. So it is somehow like a stack. I will pop from the top of it, and at the end I will push back x to the end of my array. Okay, then at the end I will push x to the end of my array. So this is how it works at all. So let me also show you the code that how maybe it's good if you see what I'm explaining in my code. So this is how it works. I have this ans, and I have a pointer that shows that what is the end of ans. Each time, and do not forget that when I am at a position, when I'm at some x, the element that is going to be added is some x, and I see that x is already in my answer. Then I can ignore this new x, because x already is in my answer. X is already in my sequence. So if it's gonna make my answer better, it already has done that before. And nothing has removed x. So nothing better than x is fun to remove x afterwards. So if x is already in, I can just ignore x. So if you look at it, I have CNTs, and each time when I'm over AI, I will say CNT of AI minus minus, so that I know that how many of each index is left in the future. First, I say that if PTR was 0, it means that I'm at the beginning, nothing is at ans. So this is the first time. If it is the first time, just say ans of PTR plus plus equal to AI, and in of AI is true. In of AI means that if AI is inside my answer or not. I say in of AI is true because it is inside my answer now. Else, if AI was inside, just continue. It is inside, so there's nothing we need to do. We can just ignore this new one. Otherwise, I say that while this is the condition that it is better if I pop the last elements. If PTR was non-zero and CNT of ans of PTR minus 1, the last element, the CNT of the last element was non-zero, and AI was better than that, better at that position, better of AI and PTR minus 1. So I have a Boolean function better. It gets two values, value and position. It says that if pose and 1, because it is 0 base, pose and 1 means that we need to minimize. It is 0 base index, not 1 base index. This is why it reversed. If pose and 1, return val must be less than ans of pose. Else return val greater than ans of pose. Okay. So it will return if this value is better at that position compared to the current one. If it was better than that, or this happened, it was better than the one before the last element, PTR need to be greater or equal to 2, and both of CNT of the last one and the CNT of the one before last, CNT of both of them must be non-zero, and AI must be better than PTR minus 2. If one of these two happened, we can pop some elements from the ends. If it was the first case, only the last elements will be popped. First, I set an in of ans of PTR minus 1 equal to false because it is not in anymore, and PTR minus minus. Else, I do this pop operation twice. In of ans of PTR minus 1 equal to false PTR minus minus, and do it once again. So this is if I'm doing pop twice. So this code is just pop. Maybe it was cleaner. If I wanted to use a clean code, I could use a pop function here, inline void of pop, and copy these two lines there. This just pops one element from the end of my stack. It says that ans of this in of that last element in the stack is false and PTR minus minus. And then I say that ans of PTR plus plus is equal to AI, I will put AI to the end of the ans, and enough AI equal to true, because now it is inside. This way, I'm greedily making the best possible sequence that I can have, and I can continue it. When I'm at the end, because I have seen all the elements and there are no elements left, by definition, I have the best possible sequence. So at the end, it's just enough to sequence all the answers. And at the end, I just set them equal to 0 once again, so that they will be initialized for the next test case. And if you do this, you will get an accepted verdict on this problem. Yes, sure. Better function that you see in here, it keeps two values, val and the position in my ans. You know, if you see, I'm first comparing AI with the last index in my ans, and then I compare AI with the one before last. So it keeps two arguments. The first one is the value of this new element. The second one is the index. So I'm seeing that if this one is better than that index or not, that index in ans or not. If that index was odd, val must be less than ans of that index, because it is zero-based indexing. When it is odd, I should minimize it, and when it is even, I should maximize it, because it starts from index 0 this time. If pose and 1, so return val less than ans of pose, other than return val greater than ans of pose. And this way, I find if it is better at that position, and just being better is not enough. I need to also make sure that these CNTs are also non-zero, so that these elements that I'm popping, I can add them once again in future. So this way, as long as I can remove some elements and make my answer better, I will do that. And I do not care about anything else, because if I make the first indices better, the next indices do not matter. Because the first priority is on the first indices. If some vertex becomes better, some index becomes better, the next indices do not matter. So I do not need to worry about how these two will be added. If their CNTs are greater than 0, they will be added somewhere. I will add them somewhere. So, and it doesn't matter that in which order they will be added, because if I make some index better, the next indices do not matter for me, that if they become worse or what. Is it clear now? If it is, please again use the emoji or put the plus in the chats. What's it called? M2. It is M2. If it is clear, please again use this emoji or put a plus. If it is not, say minus 1. Yeah, you're welcome, Kai. Thank you. Why you cannot change 3 items? Yes, we can do that, but this is a while. I just compare it with the 2 last elements, and the point is that this is a while. After that, again, it will be compared with the previous elements as well. So maybe it will pop 5 elements, 10 elements. It can remove any elements. But first, it needs to be better than these 2 last elements, and then I will compare them to the one before them. Because if it is not better than these ones, it cannot be better than the previous ones as well. Because if these ones are better, and the ones before that were worse, well, these ones themselves would pop them up. I mean, if PTR minus 1 is better than PTR minus 3, PTR minus 1 itself will pop PTR minus 3. So if this new one wants to remove PTR minus 3, first it needs to be able to remove PTR minus 1. Because there's a reason that PTR minus 1 didn't remove PTR minus 3. So this one, if it can remove PTR minus 3, it can also remove PTR minus 1. And we have a while here, not if. So we might remove 50 elements. That's possible. Is it clear? Drop whole my code, or yes, I can copy and paste the submission. Nice. So, do you have any other questions about this? If you have any other questions, let me know. Otherwise, we can move on to problem E1, which is the last problem that I solved in the contest. Well, indeed, it was the first problem that I solved in the contest, but anyway, it is maybe the hardest one. Okay, is it completely clear? Nice. Sure. So let's now, okay, move on to problem E1. Nice. Problem E1, deterministic heap. This is the easy version of the problem, and let me tell you what the statement is saying. It says that consider a perfect binary tree with size 2 to the power of n minus 1, and with nodes numbered from 1 to 2 to the power of n minus 1 and rooted at vertex 1. For vertex v, vertex 2v is its left child and vertex 2v plus 1 is its right child. Each node v also has a value a sub v assigned to it. Define the operation pop as follows. Initialize variable v as 1. Repeat the following process until vertex v is a leaf. Each time you will see its two children, you will see which one is greater than the other one. And you will swap that one with it. If they were equal, you will choose either one of them. If the two children were equal, you will choose either one of them. And this is a bad thing. You don't want this to happen, because this is not deterministic. It wants you to find the number of deterministic heaps with the specified conditions that it will say. It wants a heap that if you start from the roots and go downwards, you will never see a vertex that both of these children have the same value. You will never visit one of them. It is possible that for some vertices, their two children are the same. But in the path that you are in, you don't want to see any of them. So you compare it with its two children, and you will consider the one with the child with the maximum index, and you will swap these two. I mean, you will move that one to its parents. And at the end, you assign minus 1 to a sub b. And the max heap is deterministic if the pop operation is the deterministic to the heap when we do it only for the first time. We want to do it once, and you want it to be deterministic. So you're never faced with two children having the same value. And you can construct your heap like this. You can do an operation k times. You can do this operation of add k times. Choose an integer v, and for every vertex x on the path from 1 to v, add 1 to them. Well, this operation is useful because it keeps a heap like a heap. By doing this operation, your max heap really remains as a max heap. The parents have values greater than their children, this way. So for each vertex, when you do an operation on a vertex x, you will add 1 to all the vertices from the roots to vertex x. Okay. So now you need to find out in how many ways you can do this operation k times, such that at the end, your operation on this heap will be deterministic. Is the statement clear? Well, if you're talking about the previous problem, I just said I compared them with the last two elements, and if I can, I will remove them. And if you want, you can watch those parts again in here. I explained it in details. So is the statement of this problem F clear? If it is, please you can use this emoji or put a plus. So basically, we can choose vertices like V and add 1 to all the vertices from 1 to V. Do you have questions, Koi? Okay, if it is okay, let me If you had any issues with anything, let me know. So you can each time choose a vertex like V and add 1 to all the elements from 1 to V. So what can you do? How can you, thanks. How can you find out the number of deterministic heaps? Well, the point is that when you have some vertex, like let's call this is an arbitrary vertex like V. Assume that you have an arbitrary vertex like V, and you want the subtree of it. You want to find the number of ways that you can assign these values such that if you go the path downwards starting from V, it is gonna be a good deterministic heap. Well, the point is that when you do the operation k times, definitely the value of root is gonna be k at the end. Vertex 1 is your root, its value is gonna be k. So the value of the roots demonstrates that how many operations you've used. The value of the roots demonstrates that how many operations you have used. Because all the operations increase the value of your roots by 1. Right? So you can have, for example, 2 DPs for V. DP1 of, and about V, you do not need to keep vertex V because you have 2 to the power of n vertices, O of 2 to the power of n vertices. Instead, you can keep the height of V, h. For example, vertex V is at height h. Or you can say that if you consider its subtree, how many layers are in its subtree. So for leaves, it's gonna be 1 because there's 1 layer in their subtree. They're only themselves. And for the roots, it's gonna be n because there are n layers in their subtree. So you can keep h, which is the number of layers in their subtrees. If we want to see that for a vertex V, such that there are h layers in their subtree, how many ways do you have to apply k operations? Instead of k, let's use I. How many ways do you have to use I operations? And you know that if you use I operations in the subtree of V, the value of V itself is going to be I. Because all the operations will affect the root of the subtree. All the operations on this subtree will affect the root of this subtree. So dp1 of h and I is gonna show that what is gonna be the answer if you only use the subtree of vertex V at layer h with h layers in its subtree, and you want it to be deterministic. You want it to be deterministic. And then dp2 of h and I just says that how many ways do you have, just how many ways in total do you have to do I operations in the subtree of V. It does not have to be deterministic. So dp1 is less than or equal to dp2, its real value, not after calculating its modulo mod. But its real value is less than or equal to dp2 because dp2 is the total number of ways. dp1 is the ways that they are going to be deterministic. So these are the definitions of your dp. How can we calculate this dp? Well, the point is for the leaves, you're going to have dp1 of 1 and any I, and dp2 of 1 and any I. For the leaves, both of these values are 1 because it means that we just do I operations on a leaf. The value of that leaf is going to be 1 and there's not going to be any issue in the subtree of I. So all the ways are going to be good ways. So both of dp1 and dp2 are going to be 1. Do you agree? So for the leaves, it's going to be like this. Now assume that we want to calculate it for h greater than 1. H is at least 2. I thought the formula for combining two. I see. Sorry about that. Okay, so now let's calculate it for h equal to 2. Well, the point is that first let's talk about dp2 of h and I. This is simpler because we don't have any additional condition. And do not forget that in the statement, you know that the sum of n and k over all test cases do not exceed 500. So if you even if you have n to the power of 3 solution, n cubed solution, or n squared k solution, you can also assume that the limits for k is, because it's similar to n, let's say all of them as n. So if you have all of n cubed solution in total, it's gonna be okay with your time limits. So because the sum of n and k over all test cases is at most 500. So now what we can do, we can have another for like a, and we can say that okay, there are several cases. Either all of the operations, we know that this vertex v has 2 children. Either there was no operation on v itself, or there was some operation on v itself. If there was any operation on v itself, dp2 of h and I can be updated from dp2 of h and I minus 1. This is the case that I've done at least one operation on v itself. I said that okay, remove one of the operations that I had on v itself, just choose the other operations, and then add one additional operation on v itself. So this is dp2 of h and I will be updated from dp2 of h and I minus 1. This is if the last operation was on v itself. If there was any operation on v itself, we can assume that we've done them at last, and we say that okay, let's remove one of them and just solve it for dp2 of h and I minus 1. This is gonna be the same, the number of ways is gonna be the same. Now, if there's no operations on v itself, a operations must be on the left child, and I minus a operations will be in the right child, the subtree of the right child. And we know that the value of this vertex is gonna be a, the value of this vertex is gonna be b, which is equal to I minus a. This is the E1 problem. This is problem E1. So this value is going to be a, this is going to be b equal to I minus a. So I can say that I can have a 4 on a is going to be from 1 to I, and I can add to dp2 of h and I dp2 of h minus 1 and a, the number of times that I add a to the left child. This can also be solved using combinations, but I'm just trying to explain with dp. I mean, with dp it can be easily calculated, so there's no need to calculate any formulas as well. So I will add dp2 of h minus 1 and a by dp2 of h minus 1 and I minus a or b. Right? So this way I can calculate dp2. Either there was an operation on v itself, then dp2 of h and I is going to be updated from dp2 of h and I minus 1. If there was no operation on v, a of the operations are from the left child, I minus a operations are going to be from the right child, and I fix what is a, and I will multiply these two values. And then I'm going to say that, let's say, now I want to calculate dp1 of h and I. For dp1 of h and I need to make sure that it is deterministic. So the point is that, first of all, again like before, if I had any operation on v itself, it's going to be updated from dp of h and I minus 1. If it is not, again I have two children, there will be a operations on the left child and b operations or I minus a operations on the right child. Again, I can say that now there are several conditions when I want it to be deterministic. First of all, a must not be equal to I minus a. Otherwise, this vertex has their two children to be equal. So even in the first step, we will face with two children with their equal. So they must not be equal. So there are two cases. Either A is greater than I minus A, or A is less than I minus A. I minus A is greater than A. In this case, this left child must be deterministic if A is greater than R minus A. But the right child, for the right child, there's no limits. For the right child can be anywhere, in any way that it wants. Because I will go to the right child, to the left child in my first step. So I do not need to worry about the right child. So in this case, I need to say that dp1 of H and I will be added by dp1 of H minus 1 and A times dp2 of H and I minus A. Why I say that? Because the left child must be deterministic, because it has the greatest value and I will go to that side. But the right child does not need to be deterministic. Does not, it can be anything. Because I'm not going that way, so it can be anything. So I'm going to use dp2 for that side. And also, if A was less than I minus A, I say that dp1 of H and I, this time I say that plus equal to dp1 of H minus 1 and A, 2 of H minus 1 and A, because this left child can be anything. There's no limits on that. It's going to be dp2 of H minus 1 and A times dp1 of H minus 1 and I minus A. Because this time, this side, the right side, needs to be deterministic, and the left child does not need to be deterministic, can be anything. So the point is that this is the problem E1. The point is that for each vertex like V, you will consider the two children of V, and about them, this is for the left child and this is the right child. You know that one of them is greater. For example, assume that this A is greater than I minus A. The point is that the left child must be deterministic then. But the right child can be anything, because I will never go to the right child. So I do not need to worry about it. So I can use dp2 there. dp2 can be updated anyway. dp2, as you see, can be updated from any way that I use A operations in the left child and I minus A operations in the right child. So there's no issue with dp2. But in dp1, I need to make sure that first I only consider the cases whether A is greater than I minus A or I minus A is greater than A. I do not consider the case where they are equal, because that way it is not deterministic from the beginning. And when it was the case, if A was greater than I minus A, I will make sure that this greater child, is gonna be deterministic, and I do not need to worry about the other child. The other child can be anything. In the other case, I need to make sure that the right child is deterministic, and I do not need to worry about the left child. So this way my DPs can be updated. Thanks a lot, Mustafa. So I can say that as you see in my code, this is just as simple as it is here. I have two DPs. First of all, dp1 of 1 and I, and dp2 of 1 and I are going to be 1. Because if I have one layer, it means that there's just a leaf. It can have some value I. There's no issue with that. Then from 2 to n, I say that, first of all, I initial all the DPs to 0 back again, because now I'm calculating everything with a new mod, with a new value for P. I have to calculate them modulo a new value of P that I'm receiving now. And I first calculate dp2 of I and j like this. I have a for A from 0 to j. I say that dp2 of I and j is equal to dp2 of I and j plus dp2 of I minus 1 and A times dp2 of I minus 1 and j minus A modulo P. As you see, there are no additional constraints in here. I just care about the fact that A operations are done on the left child and B operations are done in the right child. Okay, so there's no conditions there. There's no additional conditions for DP2. But for DP1, there are more conditions. Either A must be less than J minus A or A must be greater than J minus A. They cannot be equal. And if A was less than J minus A, it is going to be dP1 of I and J plus equal to dP2 of I minus 1 and A, because there are no further constraints on the left child, times dP1 of I minus 1 and J minus A, because now I'm going to go to the right child and the subtree of right child must be deterministic, but the left child does not need to be deterministic. And if it was vice versa, it's going to be dP1 of I minus 1 and A times dP2 of I minus 1 and J minus A. And at the end, if J was non-zero, I had at least one operation. I will also consider the case that the last operation was on V itself. So I need to also add dP1 of I and J minus 1 to I, dP of I and 1 of I and J, and also dP2 of I and J minus 1 to dP2 of I and J. This is the case that I was talking about here. This is the case that the operation, I've had an operation on V itself. Then I need to add dP2 of H minus H and I minus 1 to dP2 of H and I, and dP1 of H and I minus 1 to dP1 of H and I. Is it clear? If it is clear, please again use the emoji or put a plus in the chat. If it is not, also tell me in the chat or put a minus in the chat. Nice. Do you have any questions? Okay, seems like everything is fine. So yes, these were the solutions that I've had for the problems of today's contest, and that's pretty much it. If you liked the video, I would appreciate it if you would click the like button on this video or subscribe to the channel. You do not need to have this, but if you wanted to support my work, you can do this and I would appreciate it. Also, if you want, you can join our Telegram channel. Let me put the link of our Telegram channel in the chat for further discussion in the future. And also do not forget the Friday live streams. I'm gonna have my first stream on graph algorithms this week on Friday. So thanks a lot for joining the live stream today. I once again enjoyed the opportunity to have this live stream with you. I hope I can see you next time. Thanks a lot, guys. I'm unable to solve div2 question 2, so should I practice all it? That can help, but I mostly recommend if you solve problems by rating. Sort them in Codeforces by their difficulty and try to solve the problems by their difficulty instead of just solving the second questions. That would also work, but I think difficulty works better. Thanks a lot. See you soon as well. Thank you guys. Goodbye for now.